Hello everyone, my name is Juan Ignacio Camarotti. I'm a doctoral candidate from the GECKO project at the Technical University of Munich in Germany. And today I would like to talk about my current research topic. So the title of my talk today is Robust Co-simulation Strategies Involving Isochromatic VREP Analysis in Multi-Fidelity Aerospace Application. So talking about the outline of the current presentation, we will first cover the topic of co-simulation in order to understand the motivation behind this, and also which is the main concept behind this idea. Then we will shift our attention to the main challenges for the robust co-simulation of aerospace structures using isochromatic VREP analysis. And within this, I would like to to remark two specific points in this talk. One of them is the mapping strategies that we need in order to map information between non-matching discretizations, and also the possibility of integrating multi-fidelity solvers using co-simulation approaches. And then we will conclude our talk with some conclusions and future outlook. So usually, large-scale engineering simulation are inherently multidisciplinary. So this means that we are usually dealing with coupled simulations. And in the case of aerospace application, one of the most important coupled simulations that we are usually dealing with is fluid structure interaction. So for example, here on the right, we can see an example of one phenomenon, which is called wind flutter, which is a dynamic instability happening in lightweight structures. We need to be studied, especially in the case of very high aspect ratio and high speed aircrafts. And in order to do these coupled simulations, basically, we usually have two different approaches. One of them is the monolithic approach, in which basically the two different physical domains are coupled together by solving a very big problem in which the variables coming from both domains are solved together. So here we have basically the mathematical formulation. So F and S are the let's call them the stiffness matrices coming from both domains, and we have basically on the out of the diagonal, we have the coupling matrices, which are basically in charge of coupling the two domains. This is a very stable algorithm, but has the main drawback that specialized tools need to be developed for different problems. And when we change the formulation of one of our domains, the whole problem needs to be re-implemented. And on the other side, we have the partition approach, in which both domains are solved independently. And basically, the coupling between the domains is done through the boundary conditions, which needs to be exchanged between the solvers. So basically, the partition approach is the most widely used in the industry because it allows you to use already existing solvers which were developed for each domain without the need to re-implement specific tools for coupled simulations. So basically, the idea of co-simulation is very well connected to this concept of partition approaches in multiphysics simulations. So what is co-simulation? Co-simulation is basically the process of coupling independent black solvers, which are used for, of course, different physical domains in order to simulate multiphysics problems with a dedicated tool. So here we have uh, a schema of this. We have the co-simulation tool in the middle, and we have different solvers, in this case, two different solvers, which are communicating and exchanging information between them through this co-simulation tool. So talking about which are the building blocks of this co-simulation tool, we can point out basically three different building blocks. One of them is synchronization, which is basically the coupling algorithm and the strategy to couple the solvers. Then the data exchange between the solvers. So as we see here, each solver is running in its own memory space. So data needs to be exchanged between them in order to do the coupling. And we can also point out the data transfer between the different discretizations, which is usually done through mapping techniques. And it's also important to remark that this data exchange between the solvers is usually done through inter-process communication. Let's now shift our attention to the main challenges for the robust co-simulation of aerospace structures using isochromatic discretizations. So first of all, we have a robust CAD integrated workflow, starting from the pre-processing tool where we create our geometry, then go into the analysis phase, and finally the post-processing step where we are able to analyze our results. And we also need to think that we are usually doing this in the context of optimization of the aerospace structure. So also this CAD integrated workflow needs to be aligned with the optimization scheme that we are using to optimize our geometry. Then regarding the discretization of our structure, usually we need to deal with a very large amount of patches, and usually these patches could be of high order. And in order to deal with this, we need to work with robust multi-patch coupling strategies, which allows us to couple kinematically different patches. Then we also need to be able to deal with trimming. And when we talk about trimming, we don't only talk about the the different techniques for the integration of trim elements, but we also need to talk about the problems which could appear when one performs trimming, specifically the small cut cell instability, which is a very well-known problem in the case of trimmed patches. Then we can talk about the concept of embedded structures, which is very important in aerospace engineering. We'll talk about this in some minutes. Then we need robust and scalable change formats for performing our simulations. So basically how starting from the CAD system, we create our input files in order to run the simulations. Then of course, robust mapping strategies between different discretizations when we want to do multi-physics simulations between different domains. Then of course, in the integration of different multi-fidelity solvers, that's also important, and an efficient data exchange between the solvers. So usually in aerospace structures, we need to deal with thin wall structures, which are usually modeled with shell elements, which are usually reinforced by 1D elements, which are usually modeled with beams. So in the case of finite element, this coupling of shell and beams, it's quite straightforward. But in the case of isometric analysis, you need to come up with some strategies and methodologies in order to kinematically couple these entities. So at the chair, we are basically working with a concept, which is the concept of embedded beams in shells, in which 1D entities are embedded in 2D surfaces. So this is usually the way that we work uh, to model beams which are coupled with shells. Then we can talk about the integration of different fidelity solvers. So when we are in the design phase of an aircraft, we know that the design phase is comprised of different steps, starting from the conceptual design, going to the preliminary design, and finally with the detailed design of all the structure. So when we advance in the different phases of the aircraft design, we also have the need to use different models for the analysis, which increasing accuracy and of course increasing complexity. So for example, when we look on the fluid side, in the case of fluid structure interaction problems, we start with low fidelity solvers, which are usually potential solvers like the vortex-lattice method or lifting line theory. Then we go to medium fidelity solvers like the full potential equation or Rand's model. And then we finally end up using high fidelity tools like large eddy simulations. The same with the structural solver. Usually we start with low fidelity models like a beam model for a wing, and towards the preliminary design phase, we start using more complex models like shell models reinforced with beams. So we need to be able in some way to, to couple all these different fidelity solvers using some tool. And basically this tool is the co-simulation tool that we were talking before, which allows us to couple different solvers with different level of accuracies without having to re-implement all new strategies for the coupling. Then, of course, we also need to talk about the mapping strategies. So in the case of fluid structure interaction, we usually have the fluid domain and the structure domain. On the structural domain, we need to apply the loads coming from the fluid, and on the fluid, we need to apply the displacements coming from the structure. So this transfer of information between the meshes needs to be done through some data transfer operator. Usually this data transfer operator is a mapping operator, and we need this because usually on the interface between the different domains, we are dealing with discretizations which are non-matching. So we need in some way to translate the information between the different discretization spaces. Usually, in the case of FSI simulations with IGA, one of the most used mappers is the isometric mortar mapper, which is a weak form mapper. Usually, in this, you start with the functional that you want to minimize, which is basically the difference between the solution field on one domain and on the other. You minimize this functional, you insert your discretization space for both domains, and at the end of the day, you end up with a linear system that needs to be solved in order to do the mapping. So this mapping has some drawbacks. First of all, it requires the solution of a very big linear system. It also requires the projection of the FEM or finite volume domain onto the isometric discretizations, which is also very expensive. And in the case of multi-patch geometries, a search algorithm needs to be done in order to know to which patch a node will be projected. So in order to avoid all these drawbacks, we investigated different mapping strategies like nearest neighbor or nearest element or radial basis function mapper, which are interpolation based mapper, which are less expensive than the mortar mapper. So most of my research is basically comparing all these different flavors of mapping algorithms for coupled problems. So I wouldn't lie, I don't want to delve into the this mapper, the radial basis function mapper, but we can say that basically this RBF mapper is constructing your solution field as a linear combination of coefficients times radial basis function plus a polynomial. So we were investigating this mapper because it's less computationally expensive than the mortar, and we applied this to an FSI benchmark, in this case to the FSI mock, and we obtained very good results, both in comparison with the mortar mapper and also in comparison with FEM discretizations. So finally, going to the conclusions of this talk, we talk about the multidisciplinary nature of engineering simulations, in which we're usually working with multiphysics phenomena. So we need to deal with coupling between the domains. Then we talk about co-simulation as as an integration strategy for the different solvers that are needed in a multiphysics simulation. Then we talk about the challenges in CAD-based geometries. Specifically, we point out that we need to come up with isometric analysis aware models on which we can do analyses that are meaningful. So that's an important step, and that's basically a pre-processing of our geometry. And I would like to point out that currently I'm doing an industrial secondment at Airbus Defense and Space in Ingolstadt. This started the 1st of July and is running till the end of this year. And this is enabling us a direct collaboration and validation of our CAD integrated workflow in an industrial context. So thank you very much for your attention, and I hope you enjoyed my talk.